Somewhere in the constellation Perseus, 250 million light years away, there's a supermassive black hole. And it's singing! Scientists actually recorded the note, a B-flat, 57 octaves below middle C. That's about 144 quadrillion times deeper than anything you could ever hear. The lowest note we know of anywhere in the universe. Over the next 10 minutes, I want to walk you through some of the most extreme places we found. A planet hot enough to melt lead. A moon with an alien ocean that sprays fountains into space. A weird contradiction happening on the sun's surface that physicists still can't fully explain. And a starquake that rattled Earth's atmosphere from 50,000 light years away. Let's start close to home, with Venus. It's almost the same size, mass, and makeup as Earth, basically a twin planet, and yet the two of them turned out completely differently. The reason comes down to something called the Runaway greenhouse effect. Venus's atmosphere is about 100 times heavier than ours, and it's nearly all carbon dioxide. CO2 traps heat. That's the greenhouse effect. Same thing driving climate change here. But on Venus, the atmosphere was so thick and the sun close enough that the process never leveled off. Instead of settling at a stable temperature the way Earth did, it just kept climbing until the surface hit around 465 degrees Celsius, hot enough to melt lead, tin, zinc. The pressure at ground level is 90 times Earth's, similar to what you'd feel a kilometer under the ocean. Here's the unsettling part. Venus probably had oceans once. You can still see the geological scars of it. Early on, it likely looked a lot like Earth. So what happened to all that water? It's gone. And the reason is that Venus has no global magnetic field, like Earth's molten core produces. Without that protection, the solar wind stripped away its upper atmosphere over time. Sunlight broke water vapor into hydrogen and oxygen, and the light hydrogen just drifted off into space. Slowly, the planet dried out completely.
To make things stranger, Venus spins backwards and painfully slowly. A single day there lasts 243 Earth days, longer than its entire 225-day year. So you end up with two nearly identical rocky planets, and one missing ingredient, a magnetic field, is the difference between habitable and melts lead. Send a probe down there and it'll be crushed and cooked within hours. The Soviets found that out the hard way with their Venera landers. If Venus is a story about heat destroying a planet, the icy moons of Jupiter and Saturn are the opposite. These are frozen worlds, hundreds of millions of kilometers from the sun, with surface temperatures hundreds of degrees below zero. And yet underneath all that ice, several of them are hiding oceans of liquid water. How does that even work? Basically, gravity, or more precisely, tidal heating. Think about how the moon's gravity pulls on Earth's oceans and creates tides. Now picture a moon orbiting something as massive as Jupiter. Its gravity doesn't just tug at water, it physically stretches the whole moon. And it gets more interesting. Jupiter's big moons are locked into an orbital rhythm,
where Io completes 4 orbits for every 2 Europa does, and 1 Ganymede does. That constant synchronized tugging keeps flexing their insides, and the friction from that flexing generates heat, like bending a paperclip back and forth until it warms up. On Io, closest to Jupiter, that heat is intense enough to drive non-stop volcanic eruptions. It's the most volcanically active body in the solar system. Move one moon out to Europa, and the heat is gentler, just enough to keep a global saltwater ocean liquid under an ice shell that's somewhere between 3 and 25 kilometers thick. There's more water down there than in every ocean on Earth combined. Then there's Enceladus, one of Saturn's moons. Tiny, only about 500 kilometers across, but the most reflective object in the solar system. Its surface sits near negative 200 degrees Celsius. Yet at its south pole, the ice thins out to just 1 to 5 kilometers, split by long cracks nicknamed tiger stripes. The Cassini spacecraft watched geysers erupt through those cracks, blasting water vapor into space at 800 miles per hour. It's essentially an ice volcano. What gets scientists excited isn't just that there's water, it's what's mixed in with it. Carbon dioxide, methane, ammonia, organic molecules, salts, and tiny grains of silica.
That silica is the giveaway. It forms when water reacts with hot rock, which means Enceladus likely has active hydrothermal vents on its ocean floor, similar to the ones on Earth that support entire ecosystems without any sunlight. We don't even need to land and drill. The moon is spraying samples of its own ocean straight into space, and the big question is whether there's life in it. Now let's look at the thing keeping all of us alive, the sun, and a problem on its surface that's genuinely stumped physicists for decades. Deep in the sun's core, hydrogen is fusing into helium, converting more than 4 million tons of matter into pure energy every second. But that energy doesn't just zip out. The photons carrying it bounce around inside the sun like a pinball, absorbed, re-emitted, scattered over and over for somewhere between 10,000 and 170,000 years before finally reaching the surface. That surface, the photosphere, sits around 5,500 degrees Celsius. Makes sense. That's hot. Here's where it gets strange. Move away from the surface out into the sun's outer atmosphere, and the temperature should drop. Instead, it spikes. A few thousand kilometers up in the corona, temperatures jump past 1,000,000 degrees, hundreds of times hotter than the surface below it. It's like walking away from a campfire and somehow getting hotter.
This is the coronal heating problem, and it's been puzzling scientists since 1939, when strange bright spectral lines showed up in the corona during a total solar eclipse. For a while, astronomers thought they'd found some unknown element, and even gave it a name, coronium. Turned out to be ordinary iron, but stripped of 13 of its 26 electrons, something that only happens above 1,000,000 Kelvin. That's how we know the corona really is that hot. So what's heating it? The best explanation involves magnetism. The sun's surface is constantly churning with boiling convection cells of plasma, and that motion tangles up its magnetic field lines in two main ways. First, waves. The churning surface sends magnetic waves up along the sun's field loops, and as they travel into thinner plasma, they tangle and break down into heat. Second, and more violent, magnetic braiding, where the constant motion twists field lines into tight knots. When the stress gets too high, the field snaps and reconnects, releasing energy in thousands of tiny explosions called nanoflares. Individually small, but together they're apparently enough to keep the corona at 1,000,000 degrees. It's one of solar physics' biggest open questions, and it's happening above us right now. Now imagine taking the sun's magnetism and multiplying it by roughly 1,000,000,000,000, then compressing it onto something the size of a city. That's a magnetar. Some context first. When a massive star explodes, its core can collapse into a neutron star, the mass of the sun crushed into a sphere about 20 kilometers wide, so dense that a teaspoon of it would weigh 1,000,000,000 tons. Some neutron stars also carry magnetic fields 1,000 trillion times stronger than Earth's. Those are magnetars. In late December 2004, radiation detectors around the planet suddenly lit up at once. A satellite was briefly blinded. Earth's upper atmosphere flipped from nighttime to daytime conditions almost instantly.
And the source of all this was 50,000 light years away, clear on the other side of the Milky Way. It was a magnetar called SGR 1806-20, and it had just produced the largest starquake ever recorded. Magnetars have a solid crust, and their extreme magnetic fields constantly stress that crust until, eventually, it cracks. On December 27th, that's exactly what happened, an event equivalent, roughly, to a magnitude 32 earthquake. For comparison, the devastating 2011 Japan earthquake was a magnitude 9. The crack blasted a fireball of matter and antimatter into space. In just the first tenth of a second, that burst released more energy than the sun produces in 100,000 to 150,000 years. It was, briefly, the brightest explosion ever recorded from outside our solar system, bright enough for that instant to outshine everything else in the sky combined. And then something remarkable happened afterward. The star kept vibrating, like a bell that had just been struck. By analyzing those oscillations in its X-ray light, scientists were able to map the neutron star's internal structure, its crust thickness, and the physics of matter under conditions we can't replicate anywhere on Earth. Essentially, an exploding star became a seismograph for the most extreme matter we know of. Which brings us back to that singing black hole. Galaxies like the Milky Way aren't actually the largest structures out there.
Above them sit galaxy clusters made up of hundreds or thousands of galaxies embedded in a sea of superheated gas called the intracluster medium. That gas glows in X-rays and, combined, outweighs every star in the cluster. At the center of the Perseus cluster's gas sits a supermassive black hole. As it feeds, it launches jets of plasma that inflate huge bubbles in the surrounding gas. Those bubbles push outward like a piston,
sending pressure waves rippling through the gas. Sound, essentially, moving through a medium of million-degree plasma. The Chandra X-ray telescope captured these ripples as concentric rings, and by measuring the spacing between them, astronomers worked out the frequency, a B-flat, 57 octaves below middle C, with roughly one wavefront rolling out every 10 million years. This mattered because of a puzzle astronomers had been stuck on for years. Cluster gas radiates heat away as X-rays, so by the numbers it should be cooling and collapsing inward, triggering a burst of new star formation. But observations showed almost no cold gas and almost no new stars. Something was keeping all that gas hot. Turns out, it's the black hole's sound waves. As the ripples spread outward, they become viscous and dissipate, converting back into heat. Over roughly 2.5 billion years, that slow acoustic hum balances out the cooling, the universe's most patient heating system, quietly humming a note lower than any other known in physics, holding 250 million light years of hot gas in place. So what ties all of this together? In every one of these cases, the obvious explanation falls apart, and the real answer turns out to be energy moving through a system in some non-obvious way. Venus cooked because it lost its magnetic field. Moons stay warm at minus 200 degrees Celsius because of gravity flexing their interiors. The sun's atmosphere is hotter than its own surface because of tangled magnetic fields. A dead star shook our atmosphere because its crust finally gave way. And a black hole is holding an entire galaxy cluster together by, essentially, singing to it. And we're still finding more of this. Just last year, astronomers spotted a galaxy called UHZ-1 from when the universe was under 500 million years old, already containing a black hole as massive as all the stars in its galaxy combined. Black holes that size shouldn't be able to form that fast under the standard rules, which suggests some gas clouds in the early universe collapsed straight into black holes without ever going straight through a star phase. That's really the whole story of astronomy. Every time we look closer, the universe turns out to be stranger and more extreme than we expected. Thanks for watching.